Okay, so good morning all. My name's Henry and I'm a current PhD student at Imperial College London, working in Mike's full wave research group. So as Mike mentioned, the talk I have for you this morning concerns the reconstruction of anisotropic parameters using full waveform inversion, particularly in the absence of any prior information. So this afternoon there's a talk from Adrian which deals with building acoustic velocity models with an inadequate starting model. And we believe the same is possible for a complementary anisotropy model. So it's a brief outline of the talk. So a quick motivation, then I'll present the workflow that we've developed, and then I've got the results from 2 example inversions. So the first is just a simple synthetic proof of principle, and then some results from a full-blown 3D field data inversion. So, as I'm sure everyone in the room is aware, anisotropy is prevalent in the vast majority of seismic datasets worldwide. And this anisotropy has an influence over the kinematics and the dynamics of propagating wavefronts. And as such, its consideration during inversion is critical. So with this in mind, over the past few years, there's been considerable effort invested in trying to invert for multiple parameters using full waveform inversion. So by doing this, it relaxes the requirement on pre-extracting accurate measure of anisotropy prior to full waveform inversion using expensive, intensive techniques. However, introducing more unknowns into what is already an underdetermined problem introduces a raft of new challenges. So the principle among these is how do you select the parameters that you want to update? So different combinations of parameters have different degrees of coupling, different degrees of crosstalk, and they also have different scaling characteristics. Then there's also the question of how do you update these parameters once you've chosen them. So do you do it simultaneously, sequentially, or do you flip-flop updates between them? So as Mike touched on yesterday, there doesn't really seem to be any consensus among the FWI community on how best to answer these questions, which is, I guess, is testament to the difficulty of the problem at hand. So before I press on, up on the screen, there's a quick refresher on Thomson's parameters for acoustic VTI media. So this is the parameterization I'm going to use. So the reasons for this are twofold. So partly it's for its simplicity. There's only 3 parameters. And secondly, this is considered the mode of anisotropy that's dominant in marine geology. So ignoring density, the 3 parameters we have are vertical p-wave velocity, and then 2 independent ratios that describe how velocity varies with angle from the vertical axis of symmetry. So the first of these is epsilon, which compares horizontally and vertically traveling wavefronts, and the second is delta, which compares vertical and intermediate traveling wavefronts. So these are sort of described in 2 schematics on the left. So the dashed line is for an isotropic wavefront, the black line for an anisotropic wavefront. So this is the case of elliptical anisotropy where epsilon and delta are equal. And you can see in the horizontal direction, the anisotropic wave travels faster than the isotropic wave. The little segment labeled VNMO is the inferred wave field that you would get from isotropic move-out analysis of the isotropic data. So when delta is positive, you would overestimate the velocity. In this case, where delta is negative, it's underestimated. So there's 2 simple expressions that relate the 2 Thomson parameters with vertical velocity. They're given here. So there's a simple graphic on the screen now that illustrates some of the key issues posed by multi-parameter steepest descent FWI. So we have 2 synthetic models. So on the top right, there's acoustic velocity, and down here is Thomson's epsilon parameter. So both models have a homogeneous background with a single smooth anomaly in the center. And the acquisition is in a cross-hole configuration with sources on the left and receivers on the right. So if we treat the anomaly as a single parameter and perturb it, we can see how this changes the data misfit using the objective function. And we have this plotted on the left. So epsilon changes from 0 up to 40%, and acoustic velocity from 3,000 to 4,200 meters per second. We get this very characteristic elongate elliptical valley, where the sides of the valley are much steeper than the floor. So steepest descent is going to have no problem finding the floor of the valley itself down these steep sides. But once there, the lack of gradient information means it's likely to struggle to move along it towards the global minimum, likely bouncing around, and particularly if there's noisy, there's probably going to be local minima down there. It also becomes clear that for different combinations of start model, different strategies of update would be optimal. So there's 3 scenarios up here. So for the first, we actually have a good estimate of anisotropy, and we would really want to just do a mono-parameter inversion for velocity to move towards the true answer. Conversely, for the third, we have a good measure of velocity, and we would just update epsilon. And for the second, we don't really have a good estimation of either, and we would want to update both. Without some additional information, it's not clear which strategy you would adopt for your particular scenario. So this is where we think global optimization can play a role. So global optimizations sample the model domain in a much more broad yet intelligent manner, meaning that no matter your starting position, you should be able to find a route towards the global minimum. So this leads me to the workflow that we've developed. So in terms of 3D full waveform inversion, global optimization has in the past almost ubiquitously been considered too expensive. So this is due to the huge number of candidate solutions that would need to be evaluated at each iteration over many, many iterations to get a model of sufficient resolution. But if we only consider the low wave number component of the anisotropy, then we can parameterize our model with just a handful of points, and we can spline or interpolate between these, such that global inversion now suddenly becomes more feasible. So we've sought to combine the global inversion into the framework of full waveform inversion, such that the global part updates the anisotropy, and then we have nested iterations, monoparameter steepest descent iterations, to update acoustic velocity. So these are the steps for our workflow. So we begin from just some measure of velocity, and in terms of anisotropy, we just have some bounds, some minimum and maximum. We then produce a population of candidate solutions between these bounds. For each candidate solution, we then use monoparameter steepest descent to update the p-wave velocity. And from this, we'll get some objective function value detailing the data misfit. So we use these objective function values to produce a new suite of anisotropy models using some global algorithm. And from the best anisotropy models, we take their corresponding velocity models, average them such that we have a new single velocity model for the next iteration. So we iterate like this for a handful of iterations until we're close enough to the true answer that we can then switch to conventional multi-parameter steepest descent. So from experience, we found that this works in pretty complicated models using roughly 20 candidate solutions per global iteration, 3 nested iterations per global iteration, 10 global iterations, and for the global optimization part, we elected to use quantum particle swarm optimization, or QPSO, which was developed by Soon and his collaborators in 2004. So this QPSO is essentially the evolution of PSO, which was developed in the mid-90s. So it's a branch of swarm intelligence. And the reason that we opted to use it is that it only has a single heuristic sort of tuning parameter. So it's quite simple. Importantly, we found this entire workflow, including the subsequent multi-parameter steepest descent, only increases the cost of full waveform inversion within a factor of 2. So this is partly the fact that as we're only considering the low wave number component of the anisotropy, we only need to use low frequencies. And also the fact that QPSO is easily parallelized, so that we can evaluate each candidate solution at each iteration simultaneously. So using the same L2 misfit surface that we had at the start, we can demonstrate this approach. So we have one single velocity model and a suite of random starting epsilon models indicated by the blue dots. For each of these candidate solutions, we use steepest descent to update the velocity only, such that we move downhill towards this value. The QPSO then uses the objective function values for each of these models to produce a new suite of anisotropy models. And then we take the average of the best velocity models such that we have a new population. And as we iterate, in theory, we should converge towards the global minimum. So for our proof of principle, we just got a 2D synthetic portion of everyone's favorite, the Marmousi model. So it's 2 and a bit kilometers deep, 6 kilometers wide, good turning ray coverage, 21 sources, 191 receivers, and an FWI-friendly low-frequency source. So this is the true model. And this is the epsilon model that we constructed to go with it. So it's very simple. It's just 2 features, a low epsilon anomaly at depth and a shallow high epsilon layer. But note that it's completely decoupled from the velocity model, such that the inversion should be able to tell us if there's any leakage between the 2 parameters. For a start model, we just took out the high wave number information of velocity. So just quickly to note, although this is a very good starting model for FWI, we don't see any reason why this approach can't be combined with techniques like AWI or WRI that relax this requirement for a good starting velocity model. For epsilon, we don't have any a priori information. All we have is some bounds on the minimum and maximum value for each model parameter. So I think in this case, it was just plus 20 to minus 20%. In terms of delta, we left it fixed at its true value of 0 across the model. We essentially ignore it. The reason for this is twofold. Partly, surface seismic data are almost completely insensitive to changes in delta, making its recovery very difficult. And there's also an ambiguity between delta and depth, as delta can sort of act as a depth stretching agent. So if we use this isotropy model as a start model for steepest descent multi-parameter FWI, this is the result we get. And it's not half bad. It does quite well in the shallow region, gets the high epsilon layer, although it's slightly overestimated, does very little at depth. And most importantly, we can see a lot of leakage of the high wave number information of the velocity, so the velocity structure, into this model. So this is crosstalk, and this is what we're trying to avoid. So conversely, the global approach produces a much simpler model. It's not the true answer, but it's not far off. The deep anomaly isn't quite the right shape, and the magnitude of this, the shallow layer is underestimated. But if we then use this as the start model for subsequent steepest descent multi-parameter, then it moves to this, which is much closer to the true answer. And we have much less leakage of information from the velocity into the anisotropy. There is a little bit, but it's much suppressed. So synthetics are one thing, but obviously the real value is in field data. So I've got the same example that Mike presented yesterday. So this is the same slide Mike had yesterday. So this is the acquisition map. So just to remind you, at depth, there's a fractured anticlinal chalk trap through which gas has leaked into the overburden, and we have this seismic obscured zone. So provided to us, we had some contractors models for epsilon, delta, and P-wave velocity. So these were constructed using a combination of travel time tomography and well data. So this is the epsilon model that was given to us. It's just a simple 1D, 4 or 5 layers. If we use this as the start model for steepest descent multi-parameter FWI, this is the result we get. And essentially, it's done very little. The only real update is in this layer at about 2 kilometers, where it's tried to push epsilon down towards 10%, 5%. Elsewhere, it's done very little. The global approach, however, so again, we have no a priori information, just some minimum and maximum bounds on the anisotropy. And this is the model we get. So in some respects, it's quite similar to the contractors model. In others, it's not. So in this 2 kilometer layer, it's set epsilon quite low, which is what the previous inversion was trying to do, so that's quite encouraging. But in the center of the model, where the gas cloud exists, so this vertical slice runs right through the heart of the gas cloud, it's left the anisotropy quite high. So if we use this, as before, as a start model for steepest descent multi-parameter, we get something that looks like this. And it's pushed the global model in a lot of ways towards the contractor's model, which is encouraging. It's really tightened the features of this feature where the gas cloud is, and it's pushed the magnitude of the anisotropy up higher here. So we think that this is legitimate. So in this area, we've got interbedded shales and sands. The gas is probably trapped in these sandy layers. So the VP-VS contrast between these layers is going to jump up, which is going to boost any layer-induced anisotropy in this area. Interestingly, the region where the two models are closest, the contractor's model and the inverted model, is in the center. And this is where all four of the wells were that were used to build or help build the contractor's model. So we look at the velocities that were inverted as well. So this is the local-only result, and this is the global then local result. So if I flip between the two, there's only very subtle differences in the velocity, although there's quite large contrast in the epsilon. The most noticeable feature is these artifacts, sweeping artifacts towards the edge of the model that we attribute to a combination of the finite aperture of the acquisition and possibly some long offset cycle skipping. So in the local-only result, they're much more pronounced than in the global local result, which has got to be an encouraging sign, even if we're not sure why. If we now look at a slice through this model at 2 kilometers, so the dashed line on here is where the previous vertical slice was. So this is the global then local result, and this is the local-only result. Again, the artifacts towards the edge of the model are much improved using the global local workflow. And interestingly, we also see these, in the local-only result, these artifacts leaking into the anisotropy model. So again, a sign that we have crosstalk. The anisotropy model is much simpler in the global local result, and the feature in the region of the gas cloud is very well defined. So if we look at some well data, some sonic log data taken at a position where the yellow dot is. So this is a different well to the one Mike showed yesterday. This is the raw data. If we filter this over 11 samples, so like 10 meters, it looks like this. The dashed blue line is the contractor's tomography model that we use as a start model. It matches the well data in most places, which isn't surprising, seeing as the wells were used to help build this model. The main differences are at a depth of about 1,800 meters and 2,400 meters. The start model predicts two low-velocity layers, so likely gas-charged layers, which aren't seen in the well data. So the result of the combined global-local workflow is this, and the fit is much better. It's moved the gas cloud such that the ties to the wells are much better in this zone. And in fact, across the board, at depth at the top of the anticline as well. So we've got some normalized functionals for 3 different multi-parameter steepest descent inversions, each one with a different starting anisotropy model, but the same starting velocity model. So the first case is the blue line, which is where we had an isotropic start model, so we forced epsilon and delta to 0, allowed velocity and epsilon to update. And you see this pretty quickly became unstable and fell over as the inversion tried to take the missing epsilon and put it into velocity, and it violated the stability criteria. The red line is where we use the contractor's start epsilon and delta with epsilon and velocity allowed to update. And the yellow line is where we use the global epsilon and the contractor's delta with epsilon and velocity free to update. And you can see that as the inversion proceeds across the board, there's a constant ratio of improvement when you use the global workflow. So the breaks in the worms are due to jumps in the frequency bandwidth of the inversion, which are delineated by these grey blocks. And the small jumps are because we use different subsets of sources at each iteration. So to summarize, I hope I've managed to convince at least some of you that a combined global-local workflow can overcome some of the most prominent problems associated with multi-parameter 4-waveform inversion, whilst remaining affordable. So chiefly, we believe this is down to the freedom that the inversion affords to move around the model space. Thus, you can move around local minima and seemingly also suppress some of the crosstalk between these parameters. So due to the computational limitations that the global inversion implies, we don't see the global inversion alone as an out-and-out replacement for multi-parameter FWI, but rather as complementary to it in a sequential workflow. So yeah, with that, I'd like to thank my co-authors, Mike and Adrian, the sponsors of our research consortium, both for funding my PhD and for allowing me to present the data set here. So thank you for listening.